Let's jump right back in here with rates and concentration. So one of the easiest and most informative ways to investigate a reaction is to change the concentration of the reaction and see how the initial reaction rate responds. Now, if your first question is, why do we want to look at the initial reaction rate? Why not the reaction at 5 seconds or 10 seconds? My answer to you is, why would you want to wait 10 seconds to get your answer? Essentially, it doesn't matter. Like you could do the same thing we're about to do here with the rate at 10 seconds. Just we might as well do the initial rate. It's the fastest, so there's no reason why we pick the initial, just other than it's convenient. So if we look at 6 different experiments shown at the bottom of the screen here, we have different concentrations of our two reactants in each of these experiments. Now, these experiments, they truly are completely different reactions. It's not that we had a mixture and we watched it and then we added in some extra or something and then watched it again. These are completely separate reactions that have occurred, all 6 of these, and they all started with its slightly different concentrations, and we measured the rate. And so this is the reaction that's happening, by the way. So we have ammonium and nitrite are our two reactants, and that's what we're keeping track of. That's the two concentrations that we are changing. So if we look at experiments 1 and 2, what we see is that when the ammonium doubles, keeping the nitrite the same, notice that nitrite does not change here. The reason we do this is because any change we see in the rate, then we know is for sure due only to the ammonium, because the nitrite didn't change at all. So any change we see is due to the ammonium. And what we see is that the change in the rate from 1 to 2 is that the rate doubles. So when the concentration of the ammonium doubles, the rate doubles. Interesting. Likewise, if we compare 5 and 6, so these two, in this case the ammonium is the one that stays the same, and the nitrite is the one that doubles. So the nitrite goes from 0.0404 to 0.0808, and lo and behold, the rate once again doubles. So the nitrite, when it doubles, causes a doubling of the initial rate as well. What this tells us is that the rate is proportional to the concentration of the ammonium, and the rate is proportional to the concentration of nitrite. It is directly proportional to both of those things. This proportionality, if you're unfamiliar with that, it's just saying that if two things are proportional, when something happens to one thing, the same thing happens to the other. So when one is doubled, the other is also doubled. If one is halved, the other one is also halved. That is what proportionality means. Now, proportionalities are decently useful. They certainly give us a lot more information than not knowing anything, but scientists would prefer to have an equality, not a proportionality. Equalities are much more useful because we can then do math with them that is more advanced with an equal sign than with a proportionality sign. So to get rid of a proportionality, or more accurately, to turn a proportionality into an equality, we need to introduce what's called a proportionality constant. And this is, like the name implies, it is a constant. It is a value that is not going to change. And this constant changes the proportionality into an equality. And so what we're going to do here is we're going to introduce what we call the rate constant. And this rate constant is going to change this proportionality from the equation up here into inequality. So we've now gone from having the rate is proportional to both of these concentrations to now the rate is equal to the two concentrations times some constant. Now this rate constant is going to show up for all the rest of this chapter. It's actually a really important thing to understand. It's a really important concept, the rate constant. The rate constant, roughly speaking, is a measure of the speed of a reaction. The larger the rate constant, the faster the reaction, and the smaller the rate constant, the slower the reaction. Now the values that I have here are not quite accurate, actually. So it says the slow reactions will have very small rate constants, 10 or lower. 10 isn't super slow, but it's not really fast either. So this one's not too bad. You can get rate constants down into like the 10 to the -5, 10 to the -6. You know, you can get really, really tiny rate constants. Fast reactions will have very large rate constants. So this says 10 to the 9 or higher. I actually should probably change that. I would say anything 10 to the, certainly like 10 to the 4 or 10 to the 5. Those reactions would happen so fast that, like if you started the reaction and a few seconds later you're like, oh, crud, I didn't mean to do that. Like, it's too late. The reaction is done. These reactions happen very, very fast. 10 to the 9, that reaction would literally happen faster than you can blink your eyes. Like, it's done. It's instantaneously done. That's like explosive type reaction speed. So, those values there are a little bit off, but hopefully you get the idea. I'm not going to be asking you questions, by the way, of like, here's this, you know, if you have a reaction rate law or rate constant that is, you know, 1.0 times 10 to the 2, is this fast or slow? Like, I'm not going to be asking questions like that. This is just kind of to give you a feel for the values of the rate constant. The units on a rate constant are actually going to change from one reaction to the next. Not every reaction is going to have its own unique one, but there will be multiple different units for the rate constant, just depending on how many concentration units you have in the rate law, which is what this is here, which we'll talk about, I think, actually on the next slide here. Yeah, rate law. So, the rate law shows the relationship between the reaction rate and the concentration of reactants. The exponents tell us the order of the reaction with respect to each reactant. Now you might be thinking, exponents? I didn't see any exponents. But they're hidden. They are hiding. Each of those is raised to the 1. Technically speaking, every number that you come across, if it doesn't have some other exponent, is raised to the 1. So they do actually have exponents there. Because of this, we say that the reaction is first order in each of these reactants. So it's first order in ammonium because it is raised to the 1, and it is first order in nitrite because it is raised to the 1. So then overall, because we have 1 and 1, it is second order. The reaction overall is second order. So just let me repeat that one more time. When you're taking a look at a rate law like this, you're just going to take a look at the different molecules, the concentrations that are shown, take the exponents for each of those things. The individual exponents give you the order with respect to that one part. So in this case, it is first order in respect to ammonium and first order in respect to nitrite. But then the reaction overall is all of the individual orders added together. So in this case, it is second order overall. So, and I think this is pretty much just talking about the same thing we were just saying. So the rate law for most reactions has this form. The rate is equal to the rate constant times some reactant raised to a value times some reactant raised to another value. These exponents are always going to be small whole numbers, and almost always 1 or 2. We're going to see, just as an example, I think in the next video, something that actually has fractions as the exponents here, and those are decently rare. We're really only going to see them as examples. We're not going to do too much with those. The vast majority of them are going to have 1 or 2. We'll see a little bit of 0 as well. You can have 0 as the exponent, and we'll talk about the implications of that later on. So while sometimes the reaction orders will be the same number as the coefficients in the balanced equation, this is not always the case. The reaction orders must always be calculated. You actually have to go into a lab and do an experiment to determine what the reaction order is for a particular part of a reaction. You cannot look at a balanced chemical equation and get the reaction rate or get the reaction order. It's not possible. You might get lucky every once in a while and just happen to guess, since there are so few options. Like I said, the vast majority of reactions is either 1, 2, or maybe 0. So there's really only 3 common options there. And so, if you just guess, you might get it right a third of the time. But that's not really good stats for a scientist. You don't want to be right a third of the time. You really do have to go into the lab and do the experiment. So just as an example of that, how the balanced chemical equation does not always give you the rate law. We have a few different reactions here. The first one actually does give you the rate law if you just take the balanced chemical equation and plug it into the rate law. For this one, you do get the correct rate law. For the next one, you really don't. So for the next reaction here, if we take the reactant and we look here at the rate law, the exponent is actually a fraction. It's 1.5. Now, where that comes from, we'll talk a little bit about later at the very end of this chapter. But just for now, recognize that even though in the first one here we were just able to take the balanced chemical equation and plug the reactants into the rate law and it worked out, for most of these that's not the case. So for the next one here, we have 2 into O5. If we were just plugging in the reactants into the rate law, we would expect to have a 2 as the exponent here, but we don't. It's just 1. So once again, we can't just take the balanced chemical equation. The next one here, we could. So again, like I said, sometimes it does just work out that way, but oftentimes it doesn't. So in this case, once again, just take the reactants and plug them in, and it works out. But then for the next one here, it doesn't. So you can see here in this one, you actually have a product in the rate law, which is very unusual, but is not unheard of. This is what we would, yes, autocatalytic, this bottom reaction, because the product that is being produced actually helps the reaction go faster. So it's what we call an autocatalytic reaction. So we have our 2 reactants in the rate law, but then we also have one of the products in the rate law. Okay. Let me see, do I want to go there? I think I'll save that for the next video here. So in the next one, we'll continue on talking about the same general topic here of the rate law and using information that we get from performing experiments to work out what the order of particular reactants are. So we'll see you in the next video.